All right, so this is 2.7 implicit differentiation. All right, so first of all, a couple basic things. We are going to be taking the derivative, okay? So differentiation is the verb for taking the derivative. We're going to differentiate. Now, there are two types of equations. One is explicit, and you guys probably have heard this word before, explicit. For example, explicit lyrics or explicit content, right? It's not bad. It's not necessarily that this is a bad equation, but what explicit means it's in very plain terms. There's nothing hidden. It's very in your face, very raw, very plain terms, okay? So explicit lyrics would be very raw, very plain, nothing hidden, nothing proper, nothing polite. It's just right in your face, explicit. The meaning of the word implicit, okay, well, there's lots of different meanings for implicit, but it's sort of hidden within or kind of bound within. So you would get a message implicitly would be within another message. It would be kind of wrapped up and packaged a little differently. So in math, yeah, question?
Oh, never mind. I guess you might answer it, but why do you have y on both sides?
Yeah, I'm going to be answering that. Exactly. Yeah, why to have y on both sides. So an explicit equation in math would be you have one variable, y, explained explicitly in terms of another variable, x. So explicit means that y is explained solely in terms of one variable only. It's very plain terms. There's nothing sort of packaged weirdly. There's no overlap. And this is most of the equations that we see, most of the functions that we see are explicitly laid out, okay? And we've been talking a lot about how to take the derivative of explicit functions. Now, implicit, okay, it's another way to think about this is if I have y equals, okay, part of this explanation, that is this right here, is going to be in terms of another variable, x, but it also might be explained in terms of itself as well. So it's going to be kind of all jumbled up and mixed up, okay? So implicit means that it sort of partly defines itself at times as well, okay? So if you're explaining something explicitly, then you have the terms that you're using to explain are completely separate from what the explanation is. Implicit might have the same thing that you're trying to explain inside the explanation, okay? It's not a great way to explain words or terms or concepts. If you use the word to define a word, that's not good, right? But if there is some implicit value in this thing. So you might see variables on both sides of the equation. You might see a y on both sides. You might see an x on both sides. You might see something like, I've got some examples here. You might see equations where you have, x and y on the same side, and solving for x or solving for y might be a little bit tricky. For example, this right here is the equation for a circle with radius 1 and center at the origin. So here's the origin, here's 1 unit. So the collection of points that satisfies this equation would be a circle that has radius 1 and centered at the origin. Now, to display this or to show this explicitly, we would have to solve for one or both variables. And normally we solve for y, right? So if we were to rearrange this, we would have this kind of a function. So y by itself, explained explicitly in terms of x, becomes this. And it is understood that actually this becomes two parts, the positive part and the negative part. So the top part here, like let's say the yellow part here, would be the positive or the top part of the circle, okay? And the blue part down here, the negative part, would be the bottom part of the circle. So to explain or to show the equation of a circle explicitly, y explicitly in terms of x, you'd have to come up with two different equations and map them both simultaneously. So instead of differentiating this and differentiating this, I'm going to show you how to just differentiate this. You're not going to have to split it up ahead of time. And trust me, you're going to have equations that are much more complicated than this. So defining an equation with one variable on one side and the other variable on the other side, that's not going to be reasonable. Here's a third example, or second example. Here's the next example. Check this one out, okay? Now this is a very complicated equation, and x and y are mixed up all over the place. So you can probably understand that solving for y, right, and getting it in function, f of x function form, where y is explicitly defined in terms of x, is going to be nearly impossible. It's going to be very difficult. So that process alone is going to take us a lot of time. So what I'm going to do is I'm going to show you how to go right from here to find the derivative. And the derivative might also be explained implicitly. Like y prime or dy dx might also have an x, it might have a y, it might have another y prime in there even, I don't know, we'll see. But it's going to be explained in terms of both x and y, and that's not a problem in math. Okay? So implicit differentiation, let's talk about how you actually go about doing that. Okay? So we know how to differentiate y with respect to x. We've done that, we've learned all the rules, we know how to do that. We can differentiate each term in any equation now, okay, just like normal, but I guess the thing that's different is if I want to differentiate this whole equation, it's going to have to be with respect to one of the variables only. You can't differentiate with respect to x and y at the same time. You're going to have to differentiate with respect to either x or y. Okay? So how do we do that? Let's say we have this, and I want you to write this down as an example. So we do not have to solve for y here first. We can go ahead and differentiate this, this expression here with respect to x, and I'll show you how to do that. So we're going to differentiate the whole equation, little note on the right side here, the whole equation, that is both sides of the equation. We're going to do that separately. Okay? And we're actually going to focus on each individual term in this equation. So each individual term we're going to focus on. Now, the important part that I just mentioned is that when we differentiate, you will always be asked to differentiate with respect to one of the variables, and most of the time it's going to be dx, right? So dx is going to be what I call the preferred variable. And that's the terminology that I use to help me remember that, okay, that dx, or if y was x, so the derivative of x is 1, okay? So the derivative of x with respect to x is 1, okay? We know that because x is the preferred variable. But this is where it gets tricky. Y is like a separate function. It's like a second function. And we cannot change the derivative of y into 1. Instead, we have to write the derivative of y as y prime. And I'm going to use Newton notation, not the Leibniz d dx notation mostly. So the derivative of y is y prime. The derivative of x is 1 when we are differentiating with respect to x. Okay? And this is what we're going to try to solve for when it's all said and done. Okay? So we're going to differentiate each term in this big long equation, but we're going to use all of our differentiation rules that we've learned along the way. Yeah, just throw that down there if you're done. Thanks. All right, so we're really going to differentiate each term, and this is what I'll do. I'll just kind of show this. Each term I'm going to differentiate, but I'm going to differentiate with respect to x. Okay? So let's go ahead and take a look at this. So x squared. Now the derivative of x squared, because this is, and here's the Leibniz notation, it will be helpful here, d dx, because we have only x in here, the derivative is going to be 2x. And we're done, you see? We're done. Now the derivative of y squared, or dy squared dx, okay, with respect to x, notice that we don't have an x in there. So what we're going to do is the chain rule, okay? You think about it as the chain rule, like y is a alien function, okay? So the chain rule would say I have to take 2 down, multiply it by y, subtract 1 from 2, so that's just 2y. But the chain rule says I have to also multiply by the derivative of y with respect to x, or multiply by y prime. Okay? So again, with respect to x, the derivative of this y squared term, I can't really, I can't do it the same way as if it was just an x term. So I said I wasn't going to use Leibniz notation, I apologize, but it is helpful in some cases to view it that way. Now let's just take a look at this one. Now here, this 2xy, this is all multiplied, but what you want to do is you want to see this as a product of two different functions. One x function and one y function. So in order to take the derivative of this, we are going to do product rule. The derivative of the first times the second plus the first times the derivative of the second. So the derivative of the first, because it's an x function, we're differentiating with respect to x, the derivative is plain old 2. Very good. Thanks. Right there. So the derivative of the first times the second, 2 times y, plus the first, 2x, times the derivative of the second. Well, because the second, it's a y term, it's not the preferred variable, right? So we just write y prime here. So that's the first step of implicit differentiation. You do not have to isolate for y first. You just go ahead and you differentiate each term, except wherever you see a y or have a y part of a term, then that derivative is going to be y prime. The derivative of x is going to be 1. Right? So that's the big part. The second part here now is isolating for y prime. So you see how we have a y prime here and a y prime here. I need to get these terms together on the same side of the equation and solve for y prime. And that's going to be my derivative. So now, instead of isolating at the beginning, isolating y at the beginning, now we're going to isolate the derivative of y, and that's going to be much easier. So let's get the terms over on the same side. Okay, I'm going to subtract, and I'm going to do 2y minus 2x over here. Okay, so I'm just pulling this one over and this one over. I'll factor out my y prime, so this is great. I'm going to get y prime times.
Did you take it at 2y prime?
Well, you could, but you don't have to, because you're not trying to isolate for 2y prime. You're trying to isolate for y prime. So just take out the y prime. You will be simplifying here in a bit, but you don't have to take out a 2y prime, no. Not necessarily a greatest common factor, just the y prime. All right? So when you get to this point where you have y prime just kind of all by itself here, well, this is multiplied by this expression, or this binomial, so I just divide both sides by this binomial. Okay? Okay. So is that going to be, is it same for real? Yeah. So y prime, 2y minus 2 equals 1?
Yeah.
So when you graph this function right here, it actually turns out to be just a straight line. That's why you have the derivative is equal to 1 everywhere. It doesn't matter what the x is or what the y is. So that's a case that is coincidental. That turns out to be a number. They aren't always going to turn out to be a number like this. It's usually going to be some kind of expression. Okay, let's do another example. So just copy this down. Where to go? Wait a minute. Copy this down as example number 2 right here. All right, so here's the next example. So this, again, this is actually a circle here, so example 2. This is a circle. It has, do you guys know about this? Like these are equations for circles. X squared plus y squared equals r squared. You ever heard that before? This is part of the conic sections, which I took out of our curriculum here a few years ago. Not sure why, but they
Oh,
wanted to,
wait, yeah.
I guess, leave that for another class. But anyways, yeah, so this is the equation for a circle. That's what it looks like. And if you type this in Desmos, you get a circle, and the radius is 5, because it's square root of 25. And because there's no adding or subtracting to the x here, the center of the circle is just at the origin, 0, 0. So this is a circle, center, origin, radius 5. So that's the circle like this. And that's terrible. Only slightly better. All right, so let's differentiate this, because look at what we're looking for is we're looking for an expression for a tangent line wherever I choose. Anywhere I want, I should be able to get an expression for the tangent line if I take the derivative of this. So taking the derivative implicitly means I do not have to isolate for y in terms solely of x before I begin. I can just go ahead and take the derivative of each term in this jumbled up equation. But what you have to remember is that we are finding the derivative of the y terms with respect to x, or the derivative of this whole equation with respect to x, that's our preferred variable, which means that x prime equals 1. It also means that y prime equals y prime. And that if you have a y in here, it's like treated like a different function than x. So this is how this would work. If you have a term that just has x in it, you take the derivative just like normal, that's going to be 2x. Okay, so this term, the derivative is 2x. Plus the derivative of this term. Now, what you have to envision this as is this is not the preferred variable, this is an alien function. Okay, so we'll do chain rule. We'll do 2y times the derivative of y. What's the derivative of y with respect to x? Well, that's just y prime, or dy dx. And the derivative of 25, which is a constant, is what? 0. 0. Okay? Thank you. Put it right there.
Wait, how'd you do the chain rule thing?
Okay, so the chain rule. Okay, let me pause. You said, well, how to do the chain rule here? So you could think of it two ways. I could do the chain rule for both of these. I'll do this in blue. If I did x squared, okay? So chain rule means I take care of the outside function. I do 2x to the power of 1, right? And then I multiply by the derivative of the inside function, which in this case would be 1. Because the derivative of x with respect to x is just 1. But if this was y, okay? If this was y squared, then I would write 2y to the power of 1 times the derivative of y. So the derivative of y with respect to x is not simplified to 1. It is just dy dx or y prime.
Okay.
So it's a little bit more obvious case of the chain rule.
Oh,
Technically, we do the chain rule all the time.
that's why the exponent rule works. It's just it's just the chain rule.
Yeah, yes. The power rule is basically just the chain rule with the final step multiplying by 1. Big deal. Right? Derivative of x is 1, so you don't actually have to do that step. All right, does that help?
Yes.
Okay, so now the easy part is I just have y prime here. I need to solve for y prime because that's really what I'm trying to find, dy dx. So this is going to be 2y, y prime equals negative 2x. Divide now by 2y, and y prime is negative 2x over 2y, which can be simplified to negative x over y. Negative x over y. Now, here's what's going to happen when you differentiate implicitly like this, is you're going to get the derivative in terms of both x and y, which is totally fine, because before our derivatives were only in terms of x, right? Because our functions that we took the derivatives for, are only in terms of x. So you only need the x value of the point to find the derivative. That was before. Now you might need both the x and the y coordinate to figure out what the derivative actually is. For example, the point, what's the point on this here? Let's say, so 5, 0, okay, the point 5, 0. Well, no, that's a bad one to start with. Let's do 0, 5. I know that that's this point right here. Now, what should the value of the derivative be at this point? What should it be? It's a circle. This is the very top part of the circle. What's the slope of the tangent line? It's horizontal line, so it should be 0. So let's see. Y prime evaluated at the point 0, 5 would be negative 0 divided by 5. Or 0.
Oh.
Okay?
That's fun.
Let's take a point. I'm going to take an x value of 3, and I need to find out what this y value is. Whoops, so you can see that. So I'm going to find out what this point is. It's going to be 3 something. 3 something. I don't know what it is. I'm going to use the equation to find out what the y value is. So 3 squared plus y squared equals 25. Y squared equals 25 minus 9. Y equals 16. Sorry, y squared equals 16. Y equals plus or minus 4. Let me just make some space, more space here. Got my next example already. Okay. Hello. To Papa. Oh, not responding. Excellent.
We actually did respond.
Excellent. It's going to be a big crashola here. What?
Excellent. That was so funny. You're in. That was great. Yeah, I can't take credit.
Okay, the whole computer is. Restart the program, please. All right, guys. Let me try this again. I think I was recording through that whole momentary computer freeze lapse. Not really sure. Your excellent joke.
What?
Excellent.
Excellent.
Okay. So back to this problem here. Okay, so the point is going to be 3. Look at there's 2 points on the circle. 3, 4, and 3, negative 4. You see that? Because the 2 y values. When x is 3, y is positive and negative 4. Okay? So the point 3, 4 is actually on this circle. We have a side length 3 here, a side length 4 here, and a radius of 5. That's a 3, 4, 5. That's a right triangle. Okay, so if I wanted to know what the slope was at the point 3, 4, because the derivative here is in terms of both x and y, I use the x value and the y value to find the slope of the derivative. So it's negative, x is 3, and over here, y is 4. So at the point 3, 4, the slope of the tangent line is negative 3 over 4.
Why is it negative?
Well, look at the, if you look at the diagram up here, here's the tangent line. Look at that. It's a negative slope when it touches that part of the circle.
We just ignore it, and it's a plus or minus 4.
No, you don't ignore the plus or minus 4 necessarily. The plus or minus 4 comes, that gives you the y coordinates for 2 points that are on the circle. Now this diagram is getting very, very complicated now, but let me just try this again. So at x equals 3, there are 2 points that are on the circle. 3 comma negative 4 right here, and 3 comma positive 4 right here. You see that? See that? And so the slope of the tangent line at 3 positive 4 is, slope is negative 3/4. It just so happens that over here, this slope right here will be,
Please go to the art room.
okay, so 3 negative 4 is going to be negative 3 over negative 4, which is going to be positive 3/4 for a slope. Okay?
Epic.
Good?
Yeah, no.
Yeah, no. Okay, let's do another one. Let's do another one. All right, so here's another example. Please write this down here. Let's see if I can do this without the computer really hating me. All right, here's another example. Let us differentiate this explicitly, nope, implicitly.
Oh, I'm writing that down. Even though it's not reportable. You should have written it. What? No.
Did you write D over
So
dx?
find dy dx means the same as in this notation, find y prime. Okay? With respect to x. The problem with this is you don't know which variable you're being asked to, with respect to what? It doesn't say here. So that's why this is handy. But this is y prime with respect to x.
Hey, have some respect.
Yeah, have some respect over there.
Don't be explicit.
I mean,
Be
that's
implicit.
pretty, what
Okay.
would be disrespectful?
So when we're doing this, take each term separately. This term right here is the first one we're going to tackle, and it's only in terms of x. So this is easy, just like we've always done. 5 times 2 is 10. So I'll just write 10. X to the 5 minus 1 is 4. Done. Okay. Now, this one is a little more complicated because we have an x, sort of an x function, which has a preferred variable x, and a y alien function here. So this is the non-preferred variable. So we have to do a product rule, and we have to remember that the derivative of x is 1, and the derivative of y is just y prime. So the product rule says this: I'm going to multiply the derivative of the first function times the second. So that's going to be 4x cubed, done, times the second, y. Plus the first, x to the fourth, times the derivative of the second. What's the derivative of y with respect to x? Y prime. So the derivative of this right here is this right here. Okay, I'm gonna make myself some room here. So this one here now is only in terms of y, which again, when you have to take the derivative of y, it's y prime, it's not 1. So this is gonna be 5y to the fourth, and we're gonna treat this like a chain rule where I wanna find the derivative of the inside function as well. I have to multiply by the derivative of y, which is y prime. And again, so we want to take care of every term in this equation, and the derivative of 36 is just a constant, so that is 0. So this is definitely, the first step there is definitely the most important. Yeah.
Will it ever equal like?
All right, so now, again, the second part here, the easy part, is solving for y prime. It's in two different spots, so I have to get the terms that contain the y prime, like this one and this one. I have to get them on the same side of the equation. I have to get everything else on the other side, because I'm trying to isolate now for y prime. So I'm going to write x to the fourth y prime plus 5y to the fourth y prime on the left side, and everything else is going to be on the other side. So negative 10x to the fourth minus 4x cubed y. So I just got this over to the other side, and I got this term over to the other side. Now, because I have a common factor of y prime in these two terms, I am going to remove my y prime. I'm left with x to the fourth plus 5y to the fourth. I could factor the top here, I guess. It might be a good idea to take a negative 2x cubed out of there, maybe. Negative 2x cubed, and that's going to be what? 5x plus 2y. And so the final step here, to get y prime all by itself, I want to basically divide by this term, both sides. So I want to divide by x to the fourth plus 5y to the fourth. And if you have any common factors you can simplify. If you can simplify any of this, then you probably should. You want to take a look at this, compare it maybe with your original equation, see if there's any similarities there, and that will come up later. But yeah, it looks, we can't take a common factor out of the top bottom anymore, so I think that should be your answer.
That is ugly.
Yeah, well, it looks a little ugly, yeah, but remember, now remember this, okay? Now that you have y prime isolated here, if I, and we'll continue this actually. Guys, listen. So if I sketch this original function, which I will in Desmos in a minute, if I want to find the value of the derivative at any point that's on that function, all I have to do is plug the x value in here, and down here. That's where the x value goes. I plug the y value for the same point here, and I evaluate. So it's going to be a complicated way of getting the derivative, but you can get the value of the slope of the tangent line at any point that's on the graph by plugging x and y into this expression. So also notice that the expression or the definition for the derivative also has x and y in there. Okay, so it's not just in terms of x anymore. So this is what the graph looks like. It kind of looks like it's a straight line, except we've got a little bit of a wow here, right? A wow, yeah. Okay, come on now. Oh, what's going on? Okay, anyways, so if I wanted to find the slope here of a tangent line, it looks like that for most points, except for those around the origin here, so for these points, we're going to have a pretty consistent tangent line. That looks like it's almost goes straight, doesn't it? So it looks like we have the same tangent line for any large value, but I don't know. So let's give this a quick try. Okay, let's say I want to know what is the slope of the tangent line. What's the slope at what? What's a point that's on this line? Let's find out.
4, negative 4.
I'm not sure why I can't
Into 4, negative 4.
cancel. 0, 2 is 0, 2, 0, 0, 2 to the fifth. No, not quite 2, but
Wait, what's the question?
4, negative.
I'm trying to find out. So if x is 0, that term is 0, this term is 0. You just have y fifth equals 36. So y to the fifth equals 32 would be exactly 2, but y to the fifth equals 36 would be 2 point something. I don't know why this is, I don't know why it's not letting me just find an intercept, which it always does before. So yeah, something's not working quite right.
If you just
But what's the fifth root of 36? That's going to be my value.
0, 4, 7, 6.
Sorry, you got that?
I just don't know how to work this calculator.
So 0 and, what is that?
2.0477.
Abby Flaman and Eden Batlin to the high school office.
Okay, so
Abby
if I wanted to
Flaman
find
and
the
Eden
slope
Batlin to the
here
high school office.
of this point, this should be pretty easy. All you do, guys, is you plug in, for your x value, it's going to be 0. For your y value, you put in this number. Now it's going to be approximate, but because what I'm trying to do is I'm trying to find the value of the slope at the point 0, 2.0477. So I've got 0 to the fourth here, plus 5 times this one, 2.
That's just going to be 0.
No, that's the same thing we did in chapter.
It shouldn't be 0. No, it shouldn't. It shouldn't be 0. I don't think, because we have 0 here. Sorry, we have. Oh yeah, this is actually the top is going to be. There's brackets there, so this is going to be 0 times this, which we're going to have 0 over. Doesn't matter, right? 5 times this to the fourth, so whatever that is. What's that value?
0.
No, this one.
10 points.
Doesn't really matter. No, it's not 10.
It's not
No, it's not, because it's to the fourth. You gotta do 2 to the fourth first.
Oh.
Yeah, yeah. So anyways,
23836.
what was the first number?
10.238.
No, you gotta go 2.0477 to the power of 4 first.
I didn't
Oh.
see the
Then times
special
5.
number. It's 17, and then times 5.
It's like 100,000 something, wasn't it?
7.9.
Okay, thank you. No, it's not thousands and thousands. No, 87 point. You guys gotta know how to use your calculators. Okay, but look at, because there's a 0 on top, it's 0, right? So, does that make sense? Yeah, that looks like a horizontal section of the graph there. Okay? If I plugged in this point right here, 1.5 and whatever this value is, that Desmos is not letting me find right now, then I'd plug that in, x value in for the x value, y value in for the y, and I would get a value for the slope. Okay?
But it's 0. I think I was really.
The slope here at this point is 0.
There will be a quick meeting
Yes.
for senior girls and junior girls volleyball team.
Okay, back to basics. Don't worry about equations of tangent lines just yet. Let's just get back to some basic implicit differentiation. Okay, so A, differentiate y with respect to x means I'm going to do, this is going to be 2x. This is going to be 2y times y prime, because y is not my preferred variable. So I have to do the chain rule, derivative of y is y prime. Negative 2y, y prime equals negative 2x. Y prime equals negative 2x over negative 2x. And so I have y prime equals, sorry, this is y.
Oh.
Yeah.
Negative 2x divided by negative 2y. That's just going to be x over y.
So it's
Good?
That was fun.
It's just you take the derivative of y and multiply by y prime? Is that what it is?
Well, when you have a y term, this is not, there's no x's in there.
Yeah.
So you would do like a chain rule. Do the outside, which is 2 times y to the 1. But then you have to multiply by the derivative of y, which is just y prime. So here's C. Okay, C. Watch this, guys. C. This is x times y. I'll just rewrite it so you can see it. So x times y. So I got to treat this as a product rule between this function and this function. Two different functions. So the derivative of the first is 1 times the second. Plus the first times the derivative of the second. The derivative of y is y prime. The derivative of x is 1. The derivative of y is y prime. Equals 0. So I have x y prime equals negative y divided by x, negative y over x.
Is the derivative of y squared, that'd be something different, wouldn't it?
The derivative of y squared right here
Be,
is this right here.
oh, okay.
2y times y prime.
Then y
So where do you know where to put in the y prime?
Well, you're doing chain rule.
Okay.
Think about chain
Oh,
rule. And really you're doing chain rule for every term, but look at the derivative of x squared is 2x times the derivative of x, which is just 1.
The derivative of x is 1 always?
Oh,
When you're differentiating with respect to x, yeah, the derivative of x is always 1. Because you're differentiating with respect to the variable x. So if you just have the variable x, the derivative is 1. If you're differentiating y with respect to x, then that's just the derivative of y. It's y prime. All right, one more. Which one you want to do?
E, ace.
Okay. Here's E real quick. So the derivative of x cubed is 3x squared. Done. The derivative of y cubed is 3y squared times y prime. Because that's not my preferred variable. This one is two functions. It's 6x and y. You treat it as two different functions. So the derivative of the first 6x is just 6 times the second function y. Plus the derivative of, or sorry, it's just 6x times the derivative of y. That's y prime. Now the business of getting y prime all by itself. I'm going to get the terms. Y prime. Take y prime out here. And yeah, you could factor the other side there too. But you're dividing now by 3y squared minus 6x. 3y squared minus 6x. simplify this, and then you're, if you can divide out any like terms, you should. So that's a negative 3 we'll take out there. X squared minus 2y. And take out a 3 here, and that's y squared minus 2x. Those 3's cancel out, and you're just left with a negative out front. How's that look? Look good to you guys?